introduction or something like that. I think it's like 10, 15 questions, something like that. Yeah. I haven't finished writing it yet, but it's mostly done. Any questions? Yes?
I was just wondering, can we expect any of the quizzes to be graded before the exam? Because I haven't received any quiz grades from any of those quizzes yet.
Hopefully. Yeah. I just haven't got it should have told you when you took it whether or not you got the question right.
It just says your quiz muted. There's no response to feedback, so we don't know what we got or any of our grades or anything like that associated with quizzes.
Okay. Well, your quiz grades won't affect your exam grade.
I just use quizzes like a checkpoint of my knowledge to make sure I'm on track in general. That's why I was asking.
Well, other sources of ways that you can check your knowledge are the homework, because you definitely get the answers on that.
Yeah.
And any practice that you do from the book, when the answers are in the back of the book. Yeah. Anything else? You gotta tell me what to review, otherwise I'll just stand here. Because we got a whole 2-3 weeks of stuff. Well, I guess just 2, because we're not going to do chapter 2. And I've got my computer logged in over here, so if you want me to go through any of the questions on the quiz, I can do that. Yes?
Could you go through question 1 in the quiz last week?
Yes. Just have to bring it up. Unless someone can tell me what it is. I'm going to spend today looking like a bank robber from the Wild West. So that should be under quizzes. Quiz 3. I tried to get the quizzes to just be open to show the answers if they have been graded, and I couldn't get it to do it. So all right, so question number 1, we have a transform. Show if it doesn't suck. It's a transform from R2 to R2. So among the things we know about this is it takes 2-dimensional vectors to 2-dimensional vectors. So it can be represented by a 2x2 matrix somehow. Don't know if that's what the okay, so it says it takes, this is in my version. The steps will be similar though. 5, -7. It takes it to 2, -1. And 9, 11, it takes to 5, 3. And if these two vectors are linearly independent, then they span all of R2, right? from the definitions of span and linear independence, et cetera, et cetera. And so based just on these two vectors, we should be able to figure out the entire transformation. Because if we know what it does to this and this, any other vector can be written as a linear combination of these two, then we should be able to figure out what that linear combination is and then figure out what it does to the other vectors. But it gives us the linear combination. It says T of, oh, I didn't name these. This is U. So this is T of U. And this is T of V. So this is V. 5, negative 7 is U, and 9, 11 is V. And so it says 3T of 3U minus 2V equals B. And they ask what are B1 and B2, where I'm assuming they mean the convention, this convention. So we're all in agreement that this is what they mean by this question. Okay. Well, this should be a pretty straightforward question to solve because it gives us the linear combination. And it tells us that this is a linear transformation, which means we can commute some of this stuff outside of the transformation. So T of 3U minus 2V is equal to 3 times T of U minus 2 of T, 2 times T of V. And remember, this is true because this is a linear transformation. This is not true just for functions in general. It's something special about this being a linear transformation. Sure. There we go. So T is a linear transformation. Okay, so now we just plug things in. So 3 times T of U, well, T of U is 2 minus 1 minus 2 times T of V. T of V is 5, 3. And so our answer will be 3 times this minus, let's do it in 2 steps, minus 2 times this and so that's 6 minus 10, that's minus 4, minus 3, that's minus 6, that's minus 9. And so this should be my answer, barring any mistakes in arithmetic I might have made. Which I wouldn't do on the exam because I would have my 4-function calculator at hand. Be sure that is 4-function calculator. You know what that means? The cheap ones that you can get at Walmart in the office supplies aisle? Yes?
So I was a little confused about the 4-function calculator, but my dad and I kind of tried to figure it out, and he ordered me on Amazon like an old Casio, and it has stuff like square root. Or I don't know if it has square root. We couldn't find anything with literally plus, minus, divide, multiply.
I'm using on the scientific calculator, right? And one of them have the matrix function like a TI 8384 does.
That's definitely not allowed.
Right, like a scientific one does plus, minus, divide, square root, powers, no programming functions.
I see what you mean. You have it with you.
At the end of class, what my dad ordered on Amazon.
Oh, okay.
If that works.
No, I get what you're saying. Like, it's very rare if they can only do plus, minus, the other two. Yes?
If you don't have a calculator, is it still very doable?
Yeah, it's totally doable by hand. I mean, I haven't used a calculator for any of the problems that I've tried to work out, so.
And you're giving partial credit, right?
Yeah, as long as, oh, that's a good point. Partial credit is only for the work that you show. If you get to a correct answer at the end, I don't care how you got it. I will not pay attention at all to the work that you put. I will just give you full credit. If you get an incorrect answer, I will try to work through the work that you put, so make sure I can read it, because if I can't read it, I'm just not going to bother. as far as I can get into it, I will say, well, they made it this percentage through the question, they get this percentage of credit, something like that. It's a subjective judgment, but I try to be as objective as possible. Yes.
Is this gonna be like, is there gonna be like a lot of vocab questions interspersed with like on two and one to one and like, which is reducer echelon form, stuff like that?
You'll definitely need to know those things in order to understand what the question is asking. But, I mean, these are good questions to have. I don't want to tell you what kind of questions are going to be on the exam.
I'm just wondering if there's gonna be like out of 10 questions, 2 of them are like yes and no and no partial credit.
Say that again?
I'm just wondering if like, if there's only 10 to 15 questions, it's sort of vocabulary based, doesn't have any partial credit, so it would be like, you don't know your vocab can go like 50.
Well, let me say, if everybody gets a 50 in here, I will decide that this is not an accurately representative score of the class, and I will change it so that it looks more like realistic. Yeah, it wouldn't make sense for an exam to give everybody 50%. Does that answer your question? Yeah. I'm trying to.
Sorry, I can, here's what it's, I don't know what those M plus M minus, I think that's just like.
That's totally fine.
Remember
That's
like the
100%.
number 150 or something.
So let's say if it can also do square root and it has the memory thing where it does M plus MC, M.
I mean, literally all it can display is real number, like, yeah, plus and minus numbers.
Yeah, it's just I want the requirements to be clear so that there isn't some confusion about things that are on the boundary. Like, I'm not even allowing things that are close to the boundary of what can do matrix stuff and what can't. Like, I'm being very strict about what's allowed. The other thing is that I want these questions to be easy enough that you can do them by hand anyway.
I mean, my good calculator has like a computer algebra system that does like, has matrix functions that
Definitely.
probably does everything in this class.
Very definitely not allowed.
Yeah.
We're going to do a show example or talk about through 101 on 2. I did very confident with that first time around. I'd love to review that quickly.
Yes. Let's see if I can grab an example from the book. Actually, so what are the sections? Matrix of a linear transformation. Uniqueness in existence.
Like I was reading the book last night and doing some studying, and I know that you can often use like pivots in the geometry of the matrix to make some decisions. If I'm not incorrect, but
That's yeah.
that was more of a blind understanding than it was more like a fundamental understanding of what's going on.
Yeah, I see what you're saying.
Yeah.
Is there? So someone said there was one on the quiz.
I think so.
Do you know which one? Which quiz?
The most recent one. Yeah.
Third, fourth question.
Yeah, I think it was like the third one for me. It was like a 5x3. If A is like 5x3 and there's like 3 pivots in it, is it 1-to-1 onto or both or something?
Okay. So this is a good one. Let's say A is a 5x3 matrix. Okay. So if we view this as a transformation, what does it transform? Or what are the domain and codomain? So that's a good thing to start off with. You might tell me what the domain should be? Exactly. So in order for the multiplication to be defined with a vector, these numbers have to match. So the input has to be R3, and the output will be in what?
5.
R5, yeah. So this will be, and this is looking at the geometry of it, and I'll try to explain why that makes sense. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 3, 4, 5. This is what the matrix will look like. So the actual range of this thing, all of the possible outputs that we can get from A, so just the range of A. If this is not really the right terminology, but let's think of it as a transformation. Then this thing is, I call this A1, A2, and A3. This is the span of A1, A2, and A3. Okay. So this is a 5-dimensional real space, right? That means that the minimum number of things that I can have to span the entire space is 5, right? A basis will have 5 different vectors, 5 linearly independent vectors in it. And this set only has 3, which means it does not span the entire space of R5. Does that make sense?
Yeah, you're kind of, yeah.
So we had this sort of like, we didn't completely prove it in class, but we gave kind of a loose proof that if this was, if we have a space of a certain dimension and we try to come up with vectors to span it, then the minimum number that we can have is the dimension of the space. So we have to have at least 5 vectors in order to span this space.
That makes sense. So will this end up being onto? Is that correct?
It's not onto.
Not.
Yeah, because in order for it to be onto, there has to be something that maps onto everything.
So then in that case, you'd have a pivot in every row, meaning you could find each variable?
Well, so okay, that's 2 different questions. The first one is this onto? And the answer is based on nothing about pivots so far.
Yeah.
The answer is no. It's not onto because not everything in R5 is in the span of A1, A2, and A3. The only things that we can get out of this are things that are in the span of A1, A2, and A3.
Okay.
So that's not everything because this is a 5-dimensional space. This right here is at most a 3-dimensional space. Yeah. Okay, now let's see.
So,
What does it say about pivots? I'm sorry, go ahead.
just like that's a linear transformation example, what would you call this? So when I'm looking back in my book, I can relate it better. 'Cause sometimes it's a little confusing, all the different ways they put it in the book, and a lot of stuff can look familiar. The same.
We do have a lot of related concepts. Can you hold on to this question until I finish this one?
Yeah.
Okay. So it says A has 3 pivots. So we don't quite know where they are, but we know there's one in each column. So let's say one here, here, and here. It doesn't say where. Okay. So that means that after we row reduce, we'll have something like this. So 0's here, 0's here. These will be 1s, right? So that'll be our 3 pivots. And then we can use those 1s to get rid of everything above them. So after we did a row reduction, let's say this was an augmented matrix, and we were trying to figure out what is the x, what is the input that will give us the output B. So we have two questions. The first one is the onto question, which is, can we get every single B? And the answer is no. Well, first of all, because we will get this right here, these two rows, will only correspond to things where B is equal to 0 here. Do you see what I mean by that?
So like essentially two answers are just kind of disappearing out of this.
Well, a whole space of entries, because if you had a 1 here and a 1 here, or just a 1 here, anything here, anything here, anything here, and anything here, all of those things would not be in the output.
So since it's like a three-dimensional space, we're saying it's like on the, comparing it to a plane if it were a two-dimensional space.
Yeah, exactly.
Four-dimensional space, like it's anything on that plane, but the other things are 0 that go in the other direction.
Yeah, exactly.
Okay.
Absolutely. So that's the lower dimensional subspace in R5, the smaller thing that this function is onto, but it's not onto the whole space. Some of the stuff gets left out.
That makes sense.
Yeah, just like Connor said in that example, a three-dimensional space, if we have a plane, all the stuff here above the plane and all the stuff down here below the plane, nothing maps onto that.
Yeah.
So it's not onto. I'm dying under this thing here. Okay. So that's the onto question, right? Now the one-to-one question, which is it possible to have two different x's so that, let's write it like this, ax1 equals ax2. Two different things. Now, we talked about this, and this was not in the, well, did we talk about this in the linear transformation section? Is it possible to get ax1 with equals ax2 with x1 not equal to x2? So, how should I put this? If it were one-to-one, then these two things being equal means that the outputs being equal means the inputs have to be equal. Right?
Right.
This is equivalent, based on what we talked about last time, to this matrix A being invertible. But we want to talk about this in terms of the pivots. So what can we say in terms of the pivots? I suppose if we could say that we could get two different x1 and x2s. Here's a good way to put it. Is it a good way to put it? I want to just simply say that these columns are linearly independent. Sorry, go ahead.
That's what I was going to say. In the textbook, it says if they're linearly independent, if there's no free variables, it's one-to-one, right?
Yes, that is true. I'm trying to do it straight from this definition here. How does the book explain that?
Yeah, what's the English for one-to-one?
One-to-one means it. Okay, so just like the onto, where it maps everything onto something.
Right.
One-to-one means that it maps one thing to one thing. It never maps two things to the same thing.
Will it map individual elements in the same way? Like if I have 2, 3, 0, I get 4, 6, 0. Or does it have the same behavior for all elements, or can they be? You see what I'm trying to say?
The behavior will be whatever the matrix multiplication gives you. So in that sense, excuse me, in that sense, it's always the same.
So
Yeah.
will it always
It's-
be linear transformations then, just 1-to-1, or can it be a nonlinear transformation?
Multiplication by a matrix is never a nonlinear transformation.
Okay.
So that's what we showed, that A of U plus V equals AU plus AV. Remember here, A is a matrix, which means it does something. In your example, that was just a scalar multiplication.
Right.
It doesn't always do scalar multiplication. It does other kinds of multiplication as well. Any linear combination of the columns. But it always has this property that you can distribute across addition, and if you apply it to a scalar multiple, then it commutes with the scalar multiple.
Okay.
So you do something like that.
So this example is 1-to-1 then, by definition?
This example is 1-to-1, not because of what we said here, not because it's a linear transformation.
But because it has it's linearly independent, it seems to have 3 equations and 3 variables, when you boil it down.
Yeah, but not only does it have, what you end up with is 3 equations and 3 variables, and 2 of the variables having to be fixed. They have to have a fixed value, right? These 3 variables, or these 3 equations are independent. Did you have your hand up?
That's what I was gonna say.
Okay, yeah.
Does that make sense? Okay.
So if I really try and simplify it down conceptually, like saying 1-to-1 would be like f of x equals negative x or something. So or rotate it 90 degrees counterclockwise, then you're never going to get a simple like line vector that everything's going to only have one thing that it ends up being, versus like if you said absolute value, then 1 and -1 could end up the same.
That's, yeah.
I mean, I know it's not the same thing at all, but is it like the same concept that only maps to one thing?
Let's, not that it only maps to one thing. So absolute value is an example in the real numbers. So
Or no
absolute-
2 things can map to the same thing.
That's right. That's the opposite of 1-to-1.
Yeah, that it only maps to one thing.
Yeah.
Like f of x equals.
So this is absolute value of -1 equals absolute value of 1. Even though these are 2 different inputs, they get the same output. That means that this is not 1-to-1.
Yeah.
Yeah, that's an example. Let me give an example of a matrix. So, this is what I was going to say. This, if we look at 2 outputs being the same, that's the same as saying, because of linearity, if a times x1 equals a times x2, then a times x1 minus x2 is equal to 0, right? So I just subtract this over the other side. I get ax1 minus ax2 is equal to 0. And then linearity lets me do this, right? I can go from this step to this step, which means that I can write it like this. Make sense? So these are vectors. If it's possible to multiply it by something and get 0 other than 0, that's one way to look at it.
So linearity means it's going to basically follow the rules of algebra? Or at least with plus, minus, and multiplication, division?
Certain rules of algebra.
Okay.
Just the ones that apply to vectors.
I think there's something that, like a table of that in the book, isn't
Yep.
there? Okay.
Mm-hmm. Yeah, it's anything that preserves the structure of the vector space. So additions lead to the same things, and scalar multiplications lead to the same things. But if we say that there is a non-zero vector that we can multiply a by to get 0, then that means this is not one-to-one, right? That means that any vector of this form will give us two things that map to the same thing. Okay, so an example is 1, 2, 2, 4. Now the columns in this are definitely not linearly independent, right? So if I call this A1 and this A2, then A2 minus 2A1 is equal to 0. That's a non-trivial 0 in the span, right? Okay, so these are no longer linearly independent, which means if we multiplied this by, what was that? Minus 2, 1, this would be 0.
Is minus 2, 1 just a thing that you chose just at random, or?
I chose it because it's the linear combination of these two columns that gives me 0.
Okay.
So minus 2 times A1 plus A2. That's minus 2 times this column, 1 times this column, right? And that's equal to 0 because this will be negative 2 plus 2, this will be negative 4 plus 4.
So if this is the case, is it always going to be that like A2 is some multiple of A1?
No.
So like 3 and 6, or is it?
I'm glad you asked that because this could possibly be a misleading. It's only the case when there are two vectors.
Okay.
So if there are two vectors, the only way they can be linearly dependent, which means we can do something like this, we can find a non-trivial 0, is if one of them is a multiple of the other. Now if there's more than one, let me give you an example in 3 by 3. So 1, 2, 3, 4, 5, 6, and now I have to think for a second, minus 5, minus 7, minus 9. Okay.
Yeah,
None of
I've
these
done
is
that
a scalar multiple of the other, right? And these are not linearly dependent. I mean, these are not linearly independent. They are linearly dependent because I can find a linear combination of them. This one plus this one plus this one equals 0. So it's definitely not the case. It's bigger than just scalar multiples. If I had 1, 2, 3, 2, 4, 6, and then who cares what's here? Also linearly dependent. So if you find that one column is a multiple of the other, you instantly know that they're linearly dependent because what's something that gives me 0? Minus 2, 1, and then 0. Not anything. No matter what this is, I zero this one out, and then I say this minus 2 times this, that's 0. So,
and if there are set values in the third column, does that make a difference?
no, right? Because I'm multiplying by 0, it doesn't matter. In order for it to be a non-trivial linear combination, just some of the weights have to be non-zero. So I just picked these two to be non-zero. For example, I could have like 1,000,000 columns after this. I just zero them all out. I know instantly that they're linearly dependent.
So is it that if any two columns are multiples, scalar multiples, then same concept applies, they're dependent?
Yeah. But that's just one narrow case.
But that's still, there are more cases.
There are more cases like the ones I showed before. Well, let's 1, 2, 3, and what did I have before? Well, let's just do 0, 1, 0. Okay. Now, any linear combination of these two vectors, if I want it to be linearly independent, I have to exclude all those things from here. So for example, I put 1, 3, 3 here, or let's do 1 here, 3 here, and 60. Is it obvious that this thing is a linear combination of those two?
Not to me.
Okay, so this is A1, A2. So A1 plus, so A1 plus any multiple of A2 is going to be 1 in this entry. For this entry, 3 times any multiple of A2 will be 3. So I'm totally free to pick this multiple to be whatever I want. So I pick it to be 58 A2. And now suddenly I've got this thing right here. So to get a non-trivial 0, I just subtract my A3, and all of a sudden I've got a linear combination of the columns. It's equal to 0. So yeah, the concept of linear independence is like multiples, but it's bigger. If we were only looking in 1 dimension or 2 dimensions, it would be the same thing. But in higher number of dimensions, it's a bigger concept. Okay. So that's the one-to-one and onto. Hope that's clear. Yes.
Distilling it down simply, we could say that it's onto certainly if there are no rows, all zeros or something like that, right? Would that be a rule we could, like a blanket rule we could put for that? Because that's the same as saying the system's consistent, right? Which is
that's the same as saying it's consistent.
And that's how we say that.
Couldn't you say it's onto if you have
I think
more
that's, yeah, you're right.
rows than you do columns?
If you could say it's, say that again?
If you have more rows than you do columns, wouldn't it make it onto?
Well, this is a case where we have more rows than columns, and it's not onto. It will never be onto if you have more rows than columns, because we will always be going from a smaller dimensional space into a larger dimensional space. Now, if we go the other way around, we still can't say that.
Oh, yeah, those records,
Yeah. So,
Do the opposite of what I said, would that work?
also not.
Oh, okay.
So we have to see. One of the interesting things about linear algebra and vector spaces is that we can figure out whether or not it's one-to-one and onto strictly based on the dimension of the output. So in this case, we had 3 independent vectors, so the dimension of our output was 3, which means that this 3-dimensional input goes to a 3-dimensional output inside here. And we could conclude just from that it's one-to-one. We did it in terms of saying that there's no non-trivial zeros, which is the same thing as saying the columns are linearly independent, right? And that leads us, because of linearity, to this kind of consideration, which is the definition of one-to-one. But because we know all these things are interconnected, like you were saying before, all of these similar ways of saying the same thing, different concepts, but we find that they're connected to each other. That's one of the things about linear algebra, is everything kind of simplifies down to a bunch of things being the same. And this is one of those cases. The dimension, what the dimension of the output is, will tell you everything you need to know about one-to-one and onto. So if you have a transformation from Rn to Rm, then it can only be one-to-one if n is less than or equal, well, how should I put this? And we should also say what the range of t is. So the range of t, as long as it's a linear transformation, this will also be some rk, let's say. So rk, and this sits inside our codomain, Rm. Right? This is going to be the span of the columns. Right?
So you said the transformation tells you everything you need to know about onto and one-to-one?
The dimensions that we get from it.
Okay, the dimensions, like, so n and m tell you everything you need to know?
So the range, if it's onto, this means k equals m. So the dimension of the range is the same as the dimension of the codomain. What we have here is a k-dimensional space. So if this is a plane, then it's R2, right? So in order for that plane to hit everything in this space, in the codomain, that codomain better be R2 as well, right? It can't be R1. Well, I better clarify that. It's got to be at least as big. Because if this is R1, then, well, we got a weird situation where we said the span is bigger than this.
So if you just say
Can't really happen, but
so if you have more inputs than you do, like spaces in your codomain, then you'll at least be on to. Like you'll fill up that space completely. You'll have extras that might drop off from your input, and that's okay.
well, here's the thing. Let's say we had this vector, or this matrix, 1, 2, 3, 4, 5, 6, 5, 7, 9. The example that we had earlier. So this one would be a map. It takes a three-dimensional input, right? I want to make sure I'm not going through these things so quickly that people are getting frustrated. Everybody's following along with me?
One question, you said the dimensions of what tell you everything you need to know? I think
I'm getting to that.
Yeah, okay.
So this is, the inputs for this will be three-dimensional, right? And the outputs will be three-dimensional. Right? But this is not onto. Right? Even if let's see. Even if I made this, well, we saw the example with when I have more rows than columns. Let's make more columns than rows. Let's do 6, 9, 12. So there's only two linearly independent columns in this. These two are linearly independent. But this is a combination of these two, and this is a combination of these two. This one is this one plus this one. This one is this one plus 2 times this one. Okay? So the span of the output is the span of just these two vectors. So if I call this t, then the range of t is just I shouldn't say it's R2. That's actually kind of bad. Let me change the way I talk about this. I should say the range of T is equal to the span of A1 up to AK. That's a better way to put this. So the output of this transformation is just the span of these two vectors, because these two are already in the span. They don't actually add anything else. They're not linearly independent. So this is a k-dimensional subspace of this. I'm using terminology that I probably shouldn't get to yet. Anyway, what we know is that,
Did you say A1, A2 or A1, AK?
A1 up to AK.
Okay.
So I'm just speaking in generality. This is the minimum number of vectors that's necessary to span the range.
Okay.
So when we talk about is this onto, then this K right here has to be equal to M. And in terms of pivots, that means that we have as many pivots as we have columns.
Rows, right, for onto.
Oh, for onto. Yeah. We have as many pivots as we have rows. Right. Yeah, I'm looking at this example. We can't have that because we have more rows than we have columns.
So that'd be K equals N, right? No, never mind, I'm sorry.
Yeah, M is the number of
Yeah, I'm
rows.
sorry.
Okay, and then we have to have as many, all of these vectors have to be linearly independent in order for this to be one-to-one, right? And so in that case, K has to be equal to N, and that gives us one-to-one. And this corresponds to there being a pivot in every column. Yep.
So if the matrix is gonna be one-to-one and onto, by that it has to be like a n by n matrix, right?
Yeah, exactly. Yeah, that's a good observation. The only way for it to be one-to-one and onto, or as serious mathematicians like to say, bijective, then it has to be n by n, it has to be square, and in fact it has to be invertible, which means, well, it's the same thing as saying that it's square and all of its columns are independent. Okay, so does this answer your question?
I don't even remember my question, but there's nothing that.
Well, I don't remember it
questioned
either,
about
so
at this
we're
point,
totally
So I guess
lost.
it did, but otherwise I'd still be wondering.
Okay. Good. Yeah, we figure out how many vectors it takes to span the output. That's what this row reduction algorithm does. It gets the matrix into a reduced form, which shows us how many independent columns there are, right? There's one for each pivot. And so if we have as many pivots as we have rows, that means our output is the same dimension as the span of the columns.
Okay, so I think I remember now. So the dimensions of, so basically the values of n and m tell you everything you need to know about one-to-one and one-to.
No. You also have to know if the columns are independent. How many of the columns are independent?
Okay. Gotcha.
Does this answer your question?
Keep note about it.
Okay.
Yeah, thank you.
say, if